Okay, so good afternoon. I'm happy you made it all the way to my talk, which is back online. So I won't spend too much time on introductions because in the next 45 minutes I need to show you how to build an Akka cluster that does real-time or close to real-time exercise analytics using sensors that our users will be wearing, so smartwatches, heart rate monitors, and mobile phones. So hopefully this will be a nice roundup of everything that you've learned at Scala Days, bringing together the complications of Akka, a cluster with a distributed domain, cluster-sharded domain, and distributed computation that's happening in quote-unquote real time, plus some batch processing that's happening in Spark. And of course the great news is that all of this is open source, which you can download and build yourself. So let's get on with it. Here's the thing that we're building. It's an application that has some code that's running on the watch. Now unfortunately the code that runs on the watch isn't Akka, it's not Java. In Pebble we only have about 20 kilobytes of memory for the program and for the data. So we really don't have that much maneuvering space, it's all C. The code on the mobile, that's our old friend Swift, which is sort of like Scala but uglier and more unpleasant. So let's ignore that as well. The mobile makes regular HTTP requests to our cluster. Now the cluster is a distributed domain that, cluster-sharded domain I should say, that deals with the user profiles, so someone can type in their username, password, fill in how old they are and what sort of exercises they like to do, as well as the exercises as they are happening. So all the exercises, of all the users that they have ever done and that they are doing right now. And at the bottom end of the cluster we have some distributed computation. I say distributed because quite simply the work that we have to do wouldn't fit inside one JVM. Either a single JVM would be too slow or its memory would be too limiting. So we have to spread it across more than one JVM. Now let's put some names into it and ignore the mobile and the watch code. We have a router, so think an elastic load balancer that doesn't do anything far too clever. It just receives each HTTP request and it picks a node and it forwards the request to that one node. And inside these nodes, if we were to unpack them, there are 5 main components. There is the profile cluster, and there is the exercise cluster, and then we have 3, if you like, services, these distributed computations. One that deals with the classification of the exercise, so the data from the sensors is arriving and we need to decide what sort of exercise that represents. We have push notification. Because of the nature of the system, it doesn't make sense to have, if you like, synchronous or request and in the response to receive what exercise this is. It may not be possible to do in the time we have for the request, and it might be useless to do because the app doesn't yet have enough information to decide what exercise this block of data represents. And so we have a simple push mechanism. The code that is available online, the free version, has the Apple push notification implementation. And then finally we have the program service, if you like, program computation, that runs in Spark. And it provides answers to what should the user do today. So given past history of exercises, what is the best thing to do today? So what sort of muscles to target and which intensity should the users target? And all assembled, it gives us a nice mobile exercise application. So perhaps strangely I'll begin with a demo. So we can register or log in. It's a secret password, I hope you can't see it. In any case, here it is. Here is a profile that I can fill in. I can specify what sort of sensors I have and where I wear them. This is actually really crucial to decide that I have my phone in my pocket and a watch on my hand. The suggestions that come from our batch analysis, I can click on one and the app will simply collect the values from the sensors. At this point, as a user, I would just get on with my exercise. There is no further user interaction. I don't have to press any buttons, I don't have to fill in anything, that's it. I just do my stuff. Mobile synchronizes the data from all the sensors, and suppose I'm done now, and this is the sort of result that we'll get to see. What I've done, with what intensity, and what actually I have done. So take my word for it, this is what I've been sort of flailing around while I've been recording this session. But you get the idea. This is the final result of using the app. So from your user's perspective point of view, you run the app, it will tell you what you might want to do today, what intensity you should target, and then you get on with it. No further interaction required. When you're done exercising, you stop the app on your watch or on the phone, and you get a report of what you've done. Nothing could be more simple from the user's perspective. Unfortunately, in code, it's slightly more complicated, and we'll need to take a look at that. So, here we go. Let's start with the simplest thing, which is the user profile. So, microservice, if you like, so the user profile portion of the application. So this is where we hold things like user accounts and users' names and their ages and user images, I think. And it has three main components. The profile service, so just a show of hands, who here knows and has used Spray? There we go. Right, so profile service shouldn't be at all surprising. This is a Spray route that then directs messages to the user profile processor or to the user profile. Now the user profile processor is an actor that can receive these do commands, these modification requests. So things like create an account and modify public profile. And the user profile, these are actors, also actors, spread across the cluster where I have one actor instance per user. So every user that ever uses this system will get its own instance of the user profile actor that will live somewhere in the cluster. I have one user profile processor on each node, and then I have one user profile actor living somewhere in the cluster. And the three lines here represents the Akka cluster sharding mechanism. There needs to be somehow a way to determine if I have a message that I need to send to a user profile actor, I need to find out which user profile actor I'm talking to, because I have an actor per user. So if I say I need to receive the public profile, well then it needs to go to the right actor, and only then will I get as a response that correct appropriate user's public profile. So starting with the service in code finally, this is not too surprising for anyone who's done Spray. Those of you who haven't, don't worry, this reads almost as well as Ruby or PHP. But in any case, as you can see, all the URLs begin with user, followed by extractors that say, okay, if I have a request that's user followed by some Java UUID that represents user ID, and I can add a check parameter that the mobile application requests to see that the user is still there. I can set and modify user's image. I can set and modify the user's iOS and Android device addresses for push notifications. So expanding one of these paths in more detail, let's take a look at the one that allows us to update and get the user's profile. So it's a user followed by a parameter that is a Java UUID that is extracted from the request. And now if the method is get, HTTP get, then I will complete the request by asking the user profile. Now this is, remember, individual actor somewhere in the cluster. And I need to send this individual actor that lives somewhere in the cluster the get public profile message. And I expect to get a response from that one actor of type public profile. And that completes the request. So a future of public profile completes a get request for user/UUID. And there we go, that's what the application displays. If I now want to modify a public profile, well, the method has to be a post, and it will be handled with a function that extracts an instance of public profile from the HTTP body. So the application prepares a JSON request that has the body that can be turned into an instance of public profile, and then I will send the user profile processor the message user set public profile, and I'll map write unit, which is slightly odd. So map write is simply my shortcut in using, throughout the application we're using the Scala Z's disjunct unions to represent, it's essentially a variant of either in Scala. We have an error value on the left and the right value, the correct value on the right. And in this particular case, so the map write is just a syntactical convenience for me. So I don't have to write map write of either string to unit. The key thing to notice is that the return type, if you like, the value that goes back to the client is unit. So the client will receive an HTTP 200 with no body. So all that our application does when the mobile makes a request to change the public profile, say, look, I have a 200, it worked. That's all I'm telling you. I'm not going to give you anything else as a response. Now, okay, so let's deal with the user profile process. That's the simplest actor in our entire system. There's one per node. So if I start the JVM that runs an instance of my system, I have one user profile processor. And because it's a persistent actor, I need to implement two methods, receive recover and receive command. This should be, hopefully everyone knows by now. You've suffered through 2 days of Akka and Akka persistence, so this should be not a big surprise. And so the user profile processor maintains a list of accounts. Think a map of username to user ID. And so we can implement the simplest possible scenario. When I receive a command that says someone wants to register a user account with a given email address and some password, I don't even need to know what it is, but I already have that email address in my account variable. Well, in that case, I already have that username, right? And so the only appropriate response is to say, well, this is a value on the left that says username already taken. So this will result in an HTTP 400 bad request. You're sending me something that I cannot fulfill. Okay, nice and easy. Let's deal with a slightly more complicated case. This is where I have a request for user registration with an email and a password, and the email I haven't seen yet. It is not in my known account collection. So what I'm going to do is persist the user registered event. By the time the function that replies to the sender executes, I have the event in my journal. I won't ever forget. In other words, I can make a new instance of this user profile process and replay the events and get to the same state. And by same state, I mean the same entries in the accounts variable. That's the key concept. Accounts is like an in-memory structure that says, here are all my user accounts. And I need to be able to get to that same state in case of error, when I need to remove this actor and create a new instance, or in case I need to scale out. So make more instances, more nodes, in which case they will receive a new user profile processor. All right, great. So I make a new user profile actor and I send it the user registered message. I mutate my accounts variable, save a snapshot so I don't have to replay all the messages, and reply to the sender, remember the mobile, with an HTTP 200, and the body will be the UUID of the user that I've just created. Okay. You think this is all great, this is fantastic, it works brilliantly, except imagine what would happen if we have, let's say, 3 nodes. And the first registration goes to the first node. That's all good, right? We modify our accounts variable. And so the first node is aware of this new user account that has now registered. Okay, well, let's run through another scenario. It's the second request that goes to the middle user profile process. So that's a node that needs to be created. Our monitoring has decided that it has too few nodes, and it says, right, I need to satisfy this request, I need to create a new node. Okay, JVM starts. In that JVM, we will create a new instance of the user profile processor. When it gets newly created, it receives, recovers, and so it gets to the same state that some previous version of the user profile processor was in. And so the middle one also sees the same accounts because it got created after the first one. That's all good. What about the last one, right? So the last request goes to a user profile processor that existed at the time when the first user profile processor added the account. But of course now its accounts collection is not aware of the user that's just been added. So we need to fix it somehow. So imagine that we would have some sort of bus that runs across the cluster that all these user profile processors subscribe to. And the messages that we would put on that bus are differences. So each time a user profile processor creates an account, it publishes a message on that bus that says, anyone else who's listening, modify your collection because I have created a new user account. And so in code, this could take form of the distributed pub/sub extension in Akka. Create a distributed pub/sub extension, pick a topic, so some sort of string identifier. And as part of constructing the user profile processor, I'll have it subscribe to that topic. And so every user profile processor that gets created is subscribed to this user profile processor.knownAccounts topic. And so as part of our handler to the user register message, I send a message, publish a message onto this pub/sub bus called known account added. And I need to handle that message, known account added. So if a known account added is added, has been received, if the sender is not this actor, because it wouldn't make sense to add it twice, then I'll make the mutation. And that's all perfect, right? It all works beautifully. Except, has anyone heard of this? CAP. And so good, some of you have heard. Those of you who haven't, here's the full horror. It would be really, really useful to be consistent and available and partition tolerant. Except we only get to choose two. Now, I'll run, this is a distributed system, a cluster, and I'll run it on AWS, so I need partition tolerance. My system has to survive network partitions being created. So I need to now choose two. So suppose this is $1 billion startup, I think this is the right area for such a thing. I will prefer in my design availability. Because suppose you all want to register now, then I need to be able to handle all the registration. And I will actually sacrifice consistency. By that I mean it's possible for one user profile processor on one node to not yet be aware of the changes that some other user profile processor has made. And there's nothing I can do with it. And the reality is that maybe this can be handled at the user interface actually. So if I register two users with the same email address, then when it comes to resolve the conflict, I might just forget the second user. After all, 100,000 registration, what difference does one user make? But okay, I'm being difficult. In your systems, of course, you have to decide how consistent you want to be. And as you can see, the price that you will pay for increasing consistency is decreasing availability. Anyway, okay, so this was the big discussion of the user profile processor and the profile service. Now let's get down to the individual user profile. Remember, an actor per user. And the 3 lines, they represent jiggery-pokery in technical terms, the cluster sharding mechanism. So we need to be able to, given a message, we need to be able to extract an identity of the actor that it's going to be sent to, and we need to be able to resolve a shard in which this actor will live. And that's the job for the ID extractor and shard resolver. And so the rest of the code is just like system.actorOf, except we need to also specify the ID extractor and shard resolver. So ID extractor essentially it does what I've just described. Given a message, we need to extract from it a tuple where the first element is the identity of the actor and the second element might be a different message that I will send to that actor in place of the original message. Shard resolver does exactly the same thing. Given a message, which shard, a string, does it go to? And the job for you, for your code, is to make the shards roughly equally sized. And so one of the approaches could be take the ID, make a hash code and modulo 10. That will solve it. Okay, excellent. User profile is yet another persistent actor, which means we have to implement receive command, receive recover, but in this case, I've added two states that the user profile is in. So when a user profile actor gets first created, it's in a not registered state. And it will handle only one particular message in that state. And then it will context become registered, and in that state it will handle many more messages. So imagine that a newly created user profile is like a template. This is where stuff will go to. And then stuff being the account, when I receive the account message, I'll mutate my state, remember the account username, password, and so on, and I'll context become registered. When I'm registered, I can reply to messages like get account. The thing to notice though is the handler for get account message is replying simply with what we have in memory. It doesn't go to a database, it doesn't do any more querying, it's what we know now, what's our current state. We'll reply with that immediately. So that's one of the, this is the big thing about actor-based programming and cluster sharding. You don't really need to go to another persistent store. Your event journal is your persistent store. Okay, great. Let's deal very quickly with user exercises. It will be a similar show. We have the exercise service, user exercises processor that receives all these commands that say, okay, I want to start exercising, I want to stop exercising, I have some data that I need you to decode. And it's modeled by a couple of states. So when this actor gets created, again, one per user per exercise session, then it is not exercising. When it receives the start exercising session, it moves into exercising. When in not exercising state, I can do a replay of the entire session in case I was offline. And so, there's a lot of code, but the essence is still the same. Receive a command from the API, generate and persist the event, maybe change state, and reply to the sender. So, when I'm not exercising, someone sends me an exercise session start, I persist an event and switch behavior, context become exercising, and reply to the sender with a value on the right representing the session ID. As one final example, if I'm not exercising and the client sends me an exercise session end, well, it doesn't make sense. And so I handle it by replying to it with a value on the left that says, not in a session. Well, what are you telling me? Okay. When we're exercising, let's deal with the easy cases. I can end a session, I can abandon a session, and that again results in switching behavior. The interesting stuff, the things you were all waiting for, happens in the receiving of the multi-packet. And the multi-packet represents the data that the sensors send us. This is the sort of thing that we collect. So the watch might collect an acceleration, and it might collect it at 100 samples per second. And we know that one sample is 5 bytes long. So 5 bytes per sample, 124 samples, which represents 1.2 seconds of data. And my heart rate monitor might record similar things. So it records, again, 1 byte per second now, and it has recorded 124 samples at 100 hertz sampling rate. And the mobile, remember I have my mobile, which is another thing that collects data. So if I have that in my pocket, that also collects, say, acceleration and rotation. Unfortunately, these devices like to leave gaps in the data. And so the code that we have to have on the mobile device has to pad the data, and it abstracts away this notion of real time, the wall time that you would see on the clock. And so what the server receives are blocks of data with some linear time. So block number 1, and immediately followed by block number 2. How long they took is no longer necessary as far as the server is concerned. And all the gaps will have been filled in. So that's what we receive on the server, which makes our classification logic a lot easier. Now, just the horror of what the watch sends, this is a little bit of a snippet of C. That's how we encoded the data. So there's a quick question. How many bytes in Excel data? How big is the structure? Any guesses? Well, okay, so we can probably add up, right? So it's 39 bits. And 39 bits is a bit of a silly number, so there's 1 bit of padding and the whole thing is 5 bytes long. Unfortunately, the watch is big endian CPU, and so we have to make sure that we decoded the data in the right way. And for that, we use scodec. I think Martin Odersky mentioned scodec as one of the really cool libraries that are available on the Java platform, and here it is. I can construct things like 13-bit signed big endian decoders. And then to decode 40 bits, which results in either a string, an error message on the left, or on the right, the remaining bits to be decoded and the decoded value, it's a nice application of the for comprehension. Ignore the 1 bit of padding, and then take 13 bits, 13 bits, 13 bits, and yield the remaining bits to be yet decoded, and the triple XYZ. It reads actually rather well. We can then construct sensor data decoders around it. We now have multiple data points, data sources that we can decode. Think heart rate values, rotation, acceleration, and so it makes sense to have a trait that can, given some bits, it say, well, I will probably be able to decode it, and then, of course, go ahead and decode it. And then it also makes sense to construct a root sensor data decoder that can decode multiple blocks of sensor data arriving at one time. Because of course we cannot submit data from the watch and then as another HTTP request data from the mobile. They all have to arrive at exactly the same time. And so they need to be packed together in a bigger structure. And have a convenient case, a companion object where I can apply multiple of smaller sensor data decoders and have the entire message decoded in one call. And so, the meat of it, when we are exercising, I can construct a root sensor data decoder that can decode, say, accelerometer data and heart rate data and whatever else I have. And when I receive this multi-packet, I can go ahead and decode it. So I'll take all the packets and then decode all of them, which will give me a list of either a string, the error message on the left, or on the right, sensor data with location. The problem is I don't really want to work with a list of disjunction. I would actually like a disjunction of a combined error message or a list of sensor data with location. So how do I go about that? How do I get such a thing? I'd like to flip this disjunction with the list. All I want to do is do that. Now that's easily done in my imagination. In Java code, we would fold. And finally, does anyone know what this is? No? This is actually, I'll tell you a secret, this is coming into Scala 3. This is the magic operator. It sort of works like the 3 question marks, but it generates the implementation as well. No, not really. There's a lot of code that I didn't want to type. In any case, we now have a string, an error on the left, or a list of sensor data with location. So an error might be a decoding error. The device has not sent all the data that I need. And so what do I do? Well, again, we fold. In case we have an error, we persist an event that we couldn't decode the multi-packet, and we reply to the sender with a value on the left, which will be an HTTP 400. The thing you sent me was wrong. Okay, done. If it's a value on the right, then we're in business. We have sensor data. All we have to do is send it to the exercise classifier and move on. Right, the exercise classifiers will now reply with either a fully classified exercise, or no movement, or no exercise. We persist the event. This is the same pattern repeated yet again. Now, the interesting thing is that we have 3 views. The user exercises sessions, the user exercises session and statistics. The sessions is all the sessions that the user has done. Session is the one that's currently in progress, and statistics is what's the typical behavior of a user? How often do they do such and such exercise? What's the usual intensity? The views are attached to the processor by sharing the same persistence ID, and Akka will read automatically messages from the journal and deliver them to the view. And the view receives these messages as regular events. These are events that will be delivered to the receive method. And again, we bump through multiple states. So we start by not exercising, we move into exercising, we move into in a set through context become. And the queries, again, we reply. So if someone asks us what exercises has the user done, the response is what we know, our current state. We don't have to replay anything, recompute anything, do anything extra. And we bump between the states by context becoming. Excellent. Right. Here's the interesting bit. So how do we actually get to the exercises? We have user exercises classifier and the exercise model. The exercise classifier does, if you like, signal processing. Tidies up the signal and it takes the sensor data and it constructs this human. So it knows that I have the watch on my wrist and I have my phone in my pocket and I have a heart rate monitor here. So it constructs this man with the right values attached to the right positions. We then take slices of the values that it gets sent to our machine learning, if you like, code that extracts facts. So we run the column slices, the individual data points, through our workflow, and what is produced are facts. So in this case, it's the pink, 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 followed by blue block and a red block, whatever they mean. They are some features in the data. And we feed those features, we run queries continuously on those features, we feed those queries, we run those queries through the query evaluator, feed them to a decider, and the decision, the outcome of the decision is not just what sort of exercise. It could be do one more of this, or try harder, or pick greater weight. So all that we have to do is to program it, which luckily won't be too hard, at least in concept, and I'll leave you to run through the code. So, in a different view of the flow, the user exercises classifier at the start of the pipeline, its job is to construct this human with data on the foot and the pocket and the wrist. We then run through this workflow which constructs sensor net value. This is the human, and it takes a slice of it. The slice gets fed through our workflow, and the workflow produces new facts. So we go from slices of raw data to facts, like I have this movement, I have a tap, I have no movement at all at a given sensor. Those facts get fed through the queries to the query evaluator and the decider, and then we merge the entire flow, because we have to still remember the original sender. We need to reply back to someone with, here was the exercise. We merge the entire workflow and we reply to whoever sent us the request. Okay. The thing in the green is the job for the user exercises classifier. The thing in the blue is the job for the exercise model. And so exercise model, if you like, the queries, I mean, they sound a little crazy, but it could be something as simple as at least one pink followed by at some point in the future blue. Right? Whatever pink and blue is. So this is some sort of temporal logic, which makes sense for exercises. So in case of a particular movement, I might do this movement first, followed by, I might do this movement, followed by the movement down at some point in the very near future. And that whole thing, these two facts, represent an exercise. And the decider is simply a probabilistic model. Beautifully uses a predictable. And so when I detect this movement once, it's very likely that another one will follow. In fact, it's extremely likely that 10 will follow. And after I have 10 movements for this particular user, it's extremely unlikely that an 11th one will follow, because they're just going to drop the weight and go away. So it's all fantastic. One reference that I'll throw in at the minute, I have a whole page for references later. We are able to do this because we have thrown away the concept of wall time, and we have this linear temporal logic, linear time. So we go from time block 1 to time block 2 to time block 3. We don't care what actual wall time they arrived in. They are all padded perfectly same size. And so, user exercises classifier, take the data, and all that we have to do is to construct this straw man and take the slices of it. Notice the use of the magic operator, but ultimately, for all these blocks, we pass a sensor net value to the model. We take the column slices and we slice up the data that has arrived into as many slices as we need. We say to the exercise model, do your business. The exercise model is an Akka stream, and it goes from SensorNet value to bind to sensors, which represents the facts, run it through the query evaluator, and then we make a decision. And the outcome is maybe, or rather an option of classified exercise. And so the exercise model in code is for some queries. It's an actor publisher, so it fits into the Akka stream. And we have the three components: the workflow, query evaluator, and the decider. And the exercise model actually is just a fancy workflow. Some wrapper around it, we'll see that in just a moment. We take our smaller workflow, the one that actually detects the events, classifies them, and then for every query, we feed it to the evaluator, and then we make a decision. The outcome is, as we said, an option of a fully classified exercise. See, queries come in, data goes in, runs through the workflow, we have bind to sensors with the facts, the pink, and blue, and orange, and then for each query, feed it to the query evaluator, decider, and the result is a fully classified exercise. So, this is nice and easy. An actor model is now an actor publisher. When it receives a SensorNet value, it just feeds the event, a tuple, an event on the left, and the sender on the right to the model. That's what we process. And so the easiest case is where I have no queries. If I have no queries, then clearly there will be no exercises. And so for every request that I receive, I'll just ignore it. That's it. I will not be publishing any events. Let's deal with a scenario where I have exactly one query, just a slightly more complicated scenario. So a SensorNet value arrives, we produce bind to sensors, we evaluate bind to sensors, produce query value, and hopefully produce fully classified exercise. This is yet another view of it. Remember the sender on the left. We have the sender on the right, and we have the processing on the left, on the bottom. In Akka DSL, Akka Streams DSL, this is this entire flow except rotated 90 degrees. So the actual meat is happening on the left, transform it, we evaluate it, make a decision, and join it with the sender. If we actually have a fully classified exercise, then we'll take it and send it to the sender. That's all we do. If we don't have it, we don't reply. Excellent. Slightly more the only complication, luckily we don't have to implement it ourselves, is the query evaluator. Now, to do that, we were able to use SMT, or rather CVC4, which is a theorem, first-order logic theorem prover. We didn't have to implement it. We were able to take an existing implementation with Java bindings. But we have three key things. We have a valid query, in that we can decide whether it's true or false now. We know. This was yes an event, this was no an event. Or we might get into a situation where we have satisfiable query. So this might be true or might be false in the future. So in the diagram that you've seen, one pink followed by at some point in the future blue. Suppose I've seen the one pink. Then I have a simpler query that just says blue. But I don't yet know whether the entire query is true or false. But it might be satisfiable. And then finally, I have the simplify call, which takes a query that I already have, facts that I already know, and it produces a simpler query. And an implementation in CVC4. Finally, the actual classification is a job for support vector machine. So we have a whole bunch of R code that you're free to use to train the support vector machine. What we have done is taken the code, and in this particular case, in the open source version, the only thing it will recognize, the thing that we've given you as trained data, is taps. So you can run the app and tap on the watch, and it will recognize that as an event. Training of the data is actually a fiddly and complicated process, so I'll leave you to do that. Nevertheless, ultimately it comes down to deciding a probability of a gesture. So this is the outcome of running an SVM classifier. If the probability is over some threshold, we produce a gesture at an event, which will be fed to the query evaluator, which will be fed to the decider, and out will come a fully classified exercise. And so this is the entire classification flow. This happens in quote-unquote real time. So the mobile will receive the data from from the devices, it will pad them, and we will run this exactly as the data arrives. And that's what we will use to construct the exercise model. Finally, we have these recommendations. So, when the users run the app and they say, oh, what should I do today? Well, it's job for Spark. And Spark luckily can be reading, the Spark job reads the same events that we persist. So everything that we have in the journal, we can read on the Spark side and make a decision and produce these results. The outcome of the classification is an HTTP request. So the Spark job will make an HTTP post that says, I have recommendations for you. And we're able to use the same endpoint for user-influenced recommendations. So a personal trainer can log in and say, I recommend that the user does blah. Or the Spark job can recommend the same thing. In Spark, we have actually written a suggestion job which extends our batch, but which represents the main principle. We have a job that executes every so many seconds. It operates on the Spark context, and it does this simple flow. So every 35 minutes, we look at 5 previous exercises that the user has done, and we'll attempt to predict 3 future events. So what should the user do essentially tomorrow, in the next session after that, and the session after that. And the job is actually really simple. We'll get all the eligible users, which ones should we predict this stuff for, and then we'll apply this pipeline to all those users. For those where we have results, we will submit the results to our application. So how do we do it? Well, we take the raw input data, the events, we filter them, so we might drop some users for, that don't have enough exercises yet, normalize it, predict it, we denormalize it, and that's the outcome. That's the result, right? This is what the user should do. String, double, date. Imagine string is what should the user do, double is with what intensity, date on which day. Nice and easy, just the triple that I want to submit. The way we go about it is we use a naive Bayes model for the exercises. So what should the user do? So given that the user has done, I don't know, legs on Monday and core on Tuesday and then legs again on Wednesday, what is likely that the user will do on Thursday? Oh yeah, it's probably going to be core now that I have this flow of data. And as far as intensity is concerned, we sort of assume that the users will always improve, as they all do. So they start with low intensity, they improve, and so we go, okay, well this is some sort of linear regression. And those are the 2 things we get from Spark, right? We already get a naive Bayes classifier, a naive Bayes model, and we have a linear regression model that we apply to the data that we receive from the users. And as you've seen in Dean Wampler's talk, a lot of the Spark stuff feels like Scala collections. We have things like map and collect, and all that we have to do is use them in the right way, which of course is the hard thing, but we don't have to worry about any of the mechanics. And finally, we need to submit the jobs. So we have an actor in our Spark component that submits particular jobs. So someone receives a command that says, oh, I need to run the suggestions now. So we submit the job to the Spark cluster, and we say, okay, produce the results and receive results and errors here. So don't worry about this. There is slightly more messy code. It's just so you know when you're browsing through the code as to what is happening, how exactly we've wired it together. And so, in the demo, users, when they log in, they go through the user profile processor. When they make a request to perhaps see their public profile, we go to an individual user profile actor. So the user profile actor now replies with what it has in memory. The mobile has to be aware of where the devices are so that it can construct a multi-packet that goes to the server. So I have suggestions from Spark. I'll click on one. Now what's going to happen is that the mobile is going to start receiving data from the devices. It's going to construct these multi-packets that we receive in the user profile processor. We decode them, pull out the different sensor data values. We'll send it to the user exercises classifier. The user exercises classifier is going to construct this straw man with the right values, take column slices of the data, go to the exercise model. The exercise model is going to run the classifiers, feed the data through the queries to the decider, persist the events, which the user exercises session view is going to see. And that's what we see here as a result of making an HTTP request. So, we're right on time. Are there any questions? Before you do, three key things, all the source code, everything, mobile client, all the Scala code base, all the R code, and the trained data at that URL. Jobs, we are expanding, as you may have heard, office in New York, office in London and Manchester, jobs there, and that's it, slides there. And finally, if I could recommend, once you've stopped taking pictures, if I can recommend, here's a whole bunch of things that we have used in the implementation. It's really cool to take about 6 months off to read all of this. So anyway, thank you again. I'm not sure if we have time for questions. Well, in any case, I'm here all afternoon, so come and talk to me. Thanks again.